Flutube. Get it straight.
Let's look at one final continuity problem using the Reynolds transport equation. This is a reservoir, and we're calling this a deforming control volume, which means the control volume is changing size during the course of the problem. So the control volume in this case is the volume of water in the reservoir. The reservoir is filling up, so that volume is actually changing as this surface rises. So let's take a look at a big reservoir, Lake Mead, and that's about 225 square miles in area. We're going to just say that it has the same area everywhere. It actually would decrease as you got shallower into the reservoir and it cut into the canyon. But we're going to keep it simple here. So we have a 225 square mile reservoir. We have a river that's coming in at a high flow rate, 45,000 cubic feet per second, and it's being released slowly or more slowly at 8,000 cubic feet per second. So we want to know how many feet the reservoir will rise in 24 hours. So this might be a storm happening, so there's a larger flow coming in than there is coming out. So we start the Reynolds transport theorem here, where we have, let's go straight to the part where we have the control volume, control surface parts, and they sum to zero. So whatever's happening in this control volume is related to what's coming in and what's going out. It's an incompressible fluid, water. And then one thing that's a little bit important to see here on these deformable control volumes, usually have to come up with an expression for dV. So hopefully you can look at the geometry of this problem a little bit and see that the only thing changing is the height, as long as we say that the area is constant, which we did. So dV is actually equal to this area times dH. Now, the volumes going across the control surface are just going to be uniform flows for a river going in and some outlet, maybe going through hydroelectric power tunnels. We can think of this in terms of rate of mass in, which we call m dot here. These are mass rates you can see in the textbook. In this case, that would be equal to the Q times the density. And in is negative, right? Out would be rho times Q out, and that would be positive. So we put our work on our terms here. So here's the control volume term. It's the integral of the area of the reservoir times dH, which is equal to the area times h when we do that integral. But we still have this derivative of that term, so it goes right back to being dH. So there's that kind of circular reasoning again, but it works out that way on these control volume problems sometimes when working with the volumes changing. So here we can pull the area out because it's constant, so it's rho times area times dH dt. So we take that controlled volume term, we subtract what's coming in, we add what's coming out, and it has to equal zero, sum to zero. So we can separate these terms and get the term we're interested in, which is dH dt, the change in height over time. That's simply equal to the difference in the flows divided by the reservoir surface area. We do the algebra. It also makes sense. And that comes out to be this fraction of an inch per second. So we look at it over 24 hours, and it comes up to be only about a half foot per day. So even though these are very big flows, it's a huge reservoir, so it doesn't move the level of the reservoir too quickly. So take a look again at this problem and make sure you can start to see things like this expression for dV and how to get that from the geometry. That's the important part on these, not on these deformable control volumes.